Now, actually, I should say E is approximately this, in the first 5 decimals. Since E is an irrational number, that means this decimal just keeps going on forever, never stops. And also doesn't repeat. It's not like, 2/3 is 0.66666. Okay, 0.6 repeats. Okay, but this is an irrational number. And this is the mathematical constant E. Now the reason why we're choosing this for our base is basically this. Do any of you remember, if you have a function like this, what is dy dt? Do any of you remember from your calculus, your rules of differentiation?
It's e to dt.
Just e. So that makes things very convenient for us. Makes it very easy to calculate the derivative. That's a reason why we want to use this natural exponential function, because we're dealing with derivatives, and derivatives are going to be very easy to find. Okay. And notice the shape of this function, e to the t, is going to be very similar to this shape here. The only difference is our base, instead of being 2, is 2.71828. But the general type of shape is going to be very similar to y equals 2 to t. Let me just give a slightly more formal expression for E. It's going to turn out to be useful. E is this. If you take 1 plus 1 over m, you raise this to the mth power, and you take the limit of this, as m goes to infinity, that is E. So if you like, you could use this formula to calculate E to any desired degree of vectors. Let me just illustrate this. Let's call this part f of m. Let f of m be this. 1 plus 1 over m to the m power. Now, suppose m equals 1. What would this part be? 2. Okay. You'd have 1 plus 1 over 1, that's 2 raised to the 1 power. This is 2. Suppose m equals 2. Then we would have, and you can help me out here, you would have 1 plus 1/2 squared. In other words, 1.5 squared, which is 2.25? Yep. Right, 2.25. Let's skip 3. Let's just do f of 4. What is f of 4? It would be 1 plus 1 over 4 raised to the 4th power. That would be 1.25 raised to the 4th power, which is, help me out there, 2.44. Okay, that's approximately 2.44. There's some other terms there, approximately 2.44. And if you take higher and higher values of n, the limit of this f of n will just be E. So you were already at 2.44. Suppose you took, let me just do one more. You can actually help me with this one on your calculator. What is f of 10? That would be 1.1 raised to the 10th power. What would that be? 2.593. Okay. You know, it's getting bigger and bigger. And I'll just assert, if you try, maybe we should try 100. You calculator, let's try 100. What is f of 100?
2.7.
That would be 1.01, wouldn't it, to the 100 power. Okay. Somebody over here?
2.7048.
2.7048.
Yes, sir.
Thank you. That's pretty good. See, we're getting pretty close to what I told you before. What I told you before is E is approximately 2.71828. We're getting pretty close to that. We're up above 2.7 already. So the bigger and the larger and larger M is, the closer it will get to the true value. You know, there are contests among mathematicians, usually students, saying who can express E to the most digits. I don't know how far they've gotten, but this is only the first 5. So there are probably some people who have memorized E to the first 100 digits. The winners probably have done that, maybe even more. It is an interesting number. It's hardly natural, but it's useful. These functions are very useful for explaining natural, real-world phenomena. So that's why they're the term natural. It's also very convenient because it's easy to find derivatives.
I have a question.
Yes.
What other than continuously compounding interest is it used for?
Well, actually, other than finance, there's lots. Anytime you have a growth process or that's continuous, then this would be very appropriate. And it's convenient to use because you can calculate derivatives and growth rates very easily. So for example, population growth. Population is growing more or less continuously. You know, if you take a world population, for example, probably every second there's a baby being born somewhere. So the growth is pretty much continuous. It would be very appropriate to model population as an exponential function. And the easiest one to use would be a natural exponential function. The same thing with GDP. If you think of the GDP, gross domestic product, in a big country, it's growing pretty continuously. So it makes sense to model that as an exponential function. But Zach, since you raised the topic of finance, there is an interesting discussion in Chang about an economic interpretation of E. Let me go over this. This is really an economic or finance interpretation. And let's discuss the important difference between models of discrete growth and continuous growth that I was alluding to just a minute ago. Suppose you start off with $1. And this dollar is invested at a at an annually compounded interest rate of I% per year. What would the dollar be worth at the end of 1 year if the annually compounded interest rate is I? It would be 1 times 1 plus I. That would be the value of $1 invested for 1 year at an annually compounded interest rate of I% per year. So if I were 0.05, it would be worth 1.05. If I were 0.06, it'd be worth $1.06, 1.06, etc. That's discrete growth, where the compounding occurs at the end of the year. So that's discrete. Your money is compounded every year. Okay. Now, sometimes, you don't see this too often, but sometimes you see a bank say, we're going to compound your money semi-annually. That means every 6 months, your money is going to be compounded at the end of the year. So in that case, it would be one times, you start off with $1, times 1 plus I divided by 2, raised to the 2 power. So in 6 months, they're going to give you 3%. Say I, let's say I is 6%, or 0.06. Then at the end of 6 months, you'll get I over 2 or 3. But then it'll be reinvested for another 6 months. So you'll have another 1 times I over 2. So this would be how much you would get with semi-annual compounding. This first one, let me just write in here, this is annual compounding. Well, imagine the bank compounds your money quarterly. If you have a quarterly compounding, you'd have 1 times 1 plus I over 4 to the 4th power. And that would be quarterly compounding. Every 3 months, you get 0.06 divided by 4. That would be what you would get. But there are 4 periods within the year. Well, suppose you did daily compounding. By the way, some of the credit card companies do this, daily compounding. Then, what would the formula be for daily compounding? You start off with $1, let's say.
1 times 1 plus I over 3.
Yeah. Yes, 1 plus whatever the interest rate is, divided by 365 to the 365. This would be, formula would represent how much money, let's say, you would owe them at the end of the year, if this is your annually compounded interest rate. Now this is getting pretty close to what we're thinking of when we think of continual compounding. Continual compounding would just be compounding every instant of time. So in other words, what does this remind you of? Suppose I change this. I to B, this would be a credit card company you would not want to do business with. Suppose they set the interest rate at 100%. Annual compounding, or 1. Then what would these expressions reduce to? This would reduce to 1. And what is this getting close to? What is this expression right here? Very close to? Yes, this is approximate. So that's the book's economic interpretation. In other words, suppose you have an annually compounded interest rate of 100% per year, but the compounding is continuous. Then $1 at the end of a year would be worth E dollars. Approximately 2.7128. Yeah. That's the economic interpretation that Chang gives of E. Assume the interest rate's 100%. And you start off with $1 at the end of the year, it'd be worth E dollars if you have continuous compounding every instant of time. Okay. So you want to use E when the growth process is continuous. We said earlier that if you have an equation of this type, and I won't prove this, but if you have y equals e to the t, dy dt, is just equal to e to the t. More generally, if you have an expression like this, let's generalize this. Suppose y is equal to capital A times e to the RT, where R is some constant, A is some positive constant. So we're assuming capital A is positive. We're assuming R is a constant. Could be greater than or equal to 0, but whatever it is, it's just a constant. So t is a variable, obviously. In this case right here, do any of you know what the derivative is? dy dt.
ARE to the RT.
Okay, yes. What you do, you take this expression here, this exponent, you differentiate it with respect to time. And then you multiply that times A times e to the RT. Okay. Actually, we could prove this. We could prove this. It's actually just use the chain rule. Suppose we look at this expression right here. Let's say y equals e to the w car. Then what is dy dw? Just changing notation here. What is dy dw then? Think of w as being a variable instead of t.
1W.
It's just e to the w. Right. Now, let's let w be RT. Okay. So y is a function of w, but w is a function of t. So in this setup, we could say the following. dy dt, using the chain rule, it's just dy dw times a dw dt. What is dy dw? Dy dw here is just e to the w. And dw dt is just r. Now substitute back in for w, and this is e to the RT times r. I like to put the little r first. And if you have that capital A there, it's just a coefficient, so that you just carry that along. Okay. So oftentimes we will be dealing with exponential functions of this type, where r is just a constant. Now the interpretation of little r is very important here. The interpretation is, that is the instantaneous growth rate of the function. R is the instantaneous growth rate. Suppose you have a And I'll prove that in just a minute. But let me just give you some intuition here first. Suppose you have an equation like this. Just looking at that equation, what is the growth rate of y? Let's say t is measured in years. What is the growth rate? Instantaneous growth rate.
20%.
Yep, 20%. In other words, y is growing continuously at 20% a year. Continuous growth rate. So all you have to do is look at this. If you had this, what is the growth rate of y? 5%, or 0.05, or 5%. So y would be continuously growing at 5% a year. Now, Zach, this could be the formula for a country that was experiencing significant population growth. In that case, 5 would be the current level of population, maybe 5 million people. Okay. And then the population would be growing continuously at 5% per year. And that equation might very well explain, at least for the short run, population change within the country. If you notice, if t equals 0, this term would just be e to the 0, which is 1. So our current population is whatever this number is, say 5 billion. But if t equals 1, you just plug in here and get the value of y. So I assume that you all have calculators that have the mathematical constant e. Okay. Let me just get some practice. Again, what is y at time 0? If this equation is true, it's 5. What is y of 1? Well, it would be 5 times e to the 0.05. Now, find e to the 0.05 to a few decimal places. And then multiply it by 5, and what do you get?
5.26.
5.26. Okay. So that would be the population at the end of 1 year from today. What would be the population 2 years from today? That would be y of 2. So that would be 5 times e to the 0.1. And do this calculation. What is that equal to? 5.53. So you could use this to forecast ahead what population would be in the year, assuming the population is going to grow continuously at 5%. So these functions quite useful. Okay. All right. Now, let me just prove this result. I just asserted that this little r value here is the instantaneous growth rate. Now, let me define what the instantaneous growth rate is. And notice our dependent variable here is y. So I'll call this r sub y. R sub y is the instantaneous growth rate of y. And in our previous example, y was population. Okay. More generally, it's just whatever y is. R sub y mathematically is just this. R sub y is just 1 over y times dy dt. Notice you could think of it intuitively using the concept of a differential. You can think of this as dy, the differential y, over dt. The proportional change in y per unit change in time. Or more compactly, it's just 1 over y times dy dt. Now, we know from our basic rules of differentiation, for this equation here, what is dy dt again? I think you were kind enough to give me the answer before.
For which one?
For this one up here, for the general one.
The ARE
Let's
to the
erase this.
19.
Yes. It's A times R times e to the RT. And we just proved that just a moment ago using the chain rule. What if we multiply both sides of this by 1 over y? Well, here we put a 1 over y here, so we have to divide this by y. What is y? A times e to the RT. A times e to the RT cancels out. You're just left with R. So that is a mathematical proof, really, that this R term here, that's a constant, represents the instantaneous growth rate of y at any moment in time. Instantaneous growth rate. The book talks a little bit about present value formulas, future values and present value formulas. So let me go over that concept, a very important concept in economics. Let's switch to our dependent variable being v. And let's talk about both the discrete model and a continuous model. Let V represent the future value. Then in the discrete model, what is our formula for future value? Assume that whenever we're using a discrete model, the growth rate, the discrete growth rate per year is I. So remember we were talking about interest compounding. I was the interest rate. So it was the growth rate, the annual growth rate of the money. So let's use I. If you want to find the future value of B at any time t, what is the formula, do you remember, for future value of money? A. Okay, now, we're doing discrete. You're ahead of B.
Yeah, I'm sorry.
That's all right.
I think it's A times 1 plus 1 over R times RT. Oh, raised to the RT.
Then,
A
nope,
times 1 plus I
1 plus I.
Oh, yeah.
raised to
So-
the T.
1 plus I raised to the t power. Remember earlier we were doing this letting t be 1. So it's and letting A be $1. The more general formula is this. Suppose you start off with $A now. The annual interest rate is I. So you multiply by that A times 1 plus I raised to the t power. See, if t is 1, that would just be 1 there. But if t were 2, you would have to square it. If t were 3, you'd have to cube it. Okay, yes.
Shouldn't we let it be 1 plus I over m to the mt?
Okay,
Because it's not
okay.
an annual growth rate.
We are assuming that the money is compounded annually.
Okay.
So we just use that. I is the annually compounded interest rate. Your money is compounded annually, so we don't have to divide by the m. See, if m is 1, you divide this by 1, you multiply this by 1. So
Are we just assuming that to make it simpler?
Yes.
I don't have to deal with more cases.
Yes.
Okay.
Right. So, I represents the annual growth rate. And your money is compounded, let's say annually, if we're giving this a financial context. Okay. That's the future value of money. Let me just give you an illustration. Suppose you start off with $1,000 right now. That's your A value. Suppose the interest rate is 0.05. How much would your money be worth if you leave it in the bank for 10 years? What would your $1,000 be worth in 10 years? What is the value of E? Well, the formula would just be this. And you can help me out with 1,000 times 1.05 raised to the 10th power. So what do you get when you just calculate 1.05 to the 10th power? Then move the decimal place over 3 places that you're multiplying by exactly 1,000. So what do you get?
I got 1628.
Okay.
69,
1628.
189.
Okay, yeah. Let's do that. Round it off to the nearest penny. So assuming Zach has done this calculation correct, you should check it, make sure. That would be your $1,000 would be your worth now $1,628.80. That's the future value, compound. And it's a discrete model because your money is compounding, in this case, once a year. Now, suppose we turn this problem around. Suppose you are promised, let's say $1,000, but you're going to get the $1,000 in 10 years. The interest rate is 0.05. Now, what would the formula be? Now we want to know what is the value of that future promise right now. That would be calculating the present value. And A represents the present value. So all you do, you take this formula right here. B equals A times 1 plus I to the T. And you solve for A. So just divide both sides by 1 plus I to the T. So you get A equals B divided by 1 plus I raised to the T power. Now this formula right here would be present value. So now if we flip this formula around, if you want to solve for A, it's equal to V divided by 1 plus I raised to the T power. Or another way of writing it is V times 1 plus I to the minus T power.